Good morning, everyone, and hello to one and all. In this online video, we are going to be talking about a new topic called psychophysics. We're just going to touch upon the introduction of psychophysics on how it's actually related to the concept of sensation, which is something that you have probably read in psychology. So psychophysics, it involves the determination of the psychological reaction to events that lie along a physical dimensions. So when we say psychophysics, it actually about measuring these different sensations, measuring the input that is coming from various senses. So say for example, the changes in loudness, changing in brightness, also the lightness and changes in pressure, temperature. So those kind of things and how do we really experience them, that is pretty much what the discipline of psychology about. G. Boring basically, claims that the introduction of these techniques, to measure the relationship between internal impressions, that is the psychological experience, and the external world, that is the physical events, that is what actually marked the onset of scientific psychology. So, if you remember in one of the earlier lectures, we have talked much in detail about this, that how cognitive psychology came into being, how we started really measuring what is happening in the mind space. So psychophysics is certainly at the front of the beginning of this revolution. Gustav Fechner formalized the psychophysical methods, which measure attributes of the world in terms of their psychological values. His methods, which are detailed later in the chapter, show that psychological judgments varied in particular ways to the intensity of the stimulus and the particular sensory modality of the stimulus. So, say for example, the judgments of visual stimuli differed from judgments of auditory stimuli, which differed also from judgments of taste stimuli, and so on. So, since these relations held at least approximately for many different people, Fechner and other researchers concluded that private internal judgments had been measured accurately. So, as shown in Figure 6.1, psychophysicists could measure the psychological attributes of brightness, the loudness, and also the heaviness and pain, just as physicists measure the corresponding physical attributes of light intensity, the auditory intensity, and so on. So the psychophysical relation between stimulus and judgment depends on the particular sensory modality that is stimulated. The pain judgments in response to increase in electrical intensity of shocks will apply to the skin grow much more rapidly than do loudness judgments in response to increases in sound energy. So, for one shock to be judged twice as painful as another, the intensity of the shock needs to have been increased about one third. So, we can see then that merely measuring changes in physical units doesn't always help us accurately determine changes in psychological units. In this chapter, psychophysical methods are used to illustrate three scientific topics. First, we have operational definitions, which describe the procedures used to produce a concept and allow us to communicate successfully about the concepts we are studying. So, when we say operational definition, it is what does it mean when a subject reports that he or she detects a painful stimulus? So therefore, an operational definitions of detection and one of pain will help to ensure that scientists use technical terms in similar ways. So a related issue has to do with measurement scales, which is the assignment of numbers or names to objects and their attributes. So in measurement scales, it is how do we determine whether one light intensity appears twice as bright as another. So, not all psychophysical techniques permit accurate statements about the ratio of one sensation to another. So finally, we shall discuss the small n designs, or those based on small numbers of subjects. So in this context, we explain why it is often appropriate to formulate psychophysical laws that are based on large numbers of observations, but that are taken from a small number of observers, which is the small n. So this technique differs from that often used in psychology experiments, in which large numbers of subjects are used but few observations are taken on each person. So in the following sections, we discuss the operational definition of a theoretical construct called a threshold. So in common language, a threshold is the part of a doorway you step through or over to enter a room. So the classical physicists believe that stimuli had to cross such a barrier to enter the brain or the mind. So if a stimulus were strong, it could easily jump over the threshold. So a crude analogy that may be helpful is to think of the stimulus as a pole vaulter. So the bar corresponds to the threshold. So a good jump will put you over the bar across the threshold, whereas a feeble jump will not. So the question then is one of how strong a stimulus must be if a signal is to cross the threshold. So, answering this question was of major concern to classical psychophysicists. So, at first, the answer may seem obvious, where all we have to do is slowly increase the intensity of a stimulus, such as a tone or a dim light, until the observer responds, yes, there it is. So unfortunately, when we try to repeat this process, the point at which an observer suddenly detects the stimulus changes from trial to trial. So to deal with this variability, classical psychophysicists develop statistical methods to estimate the best value for the threshold. So, we will discuss only one of the methods developed by Fechner and known as the methods of limits. So, a method of limits, it is an experimental technique which is used to determine the threshold of sensory feeling by either gradually increasing or decreasing the magnitude of the stimulus. So, if we perform an experiment using the method of limits to determine the threshold for a tone, the results would look like those shown in table 6.1, which is the method of limits to determine an absolute threshold. So, in the table 6.1, each column represent data from one block of trials. So the first block starts with a clearly audible tone to which the observer responds yes. So as you can see, the tone intensity is lowered in successive steps until the observer reports no, thus ending that trial block. So the next block of trials starts with an intensity so low that the observer cannot hear the tone and response no. So on successive trials, the intensities gradually increase until the observer reports hearing the tone. So this process of alternating trial blocks continues until table 6.1 is complete. So each block is started at different intensity to avoid extra cues that might mislead the observer. So if the observer were a perfect stimulus detector, the point at which responses switch from yes to no or vice versa. So it would always be the same. So this ideal point would be the threshold. So the stimuli less intense than this value would never be detected, and the stimuli greater than or equal to this ideal threshold would always be detected. So unfortunately, real data from real people do not have these ideal characteristics. Instead, they look like the data in table 6.1. So the observers are influenced by the expectations about when they think it is time to change the response from yes to no or vice versa. Say for example, if a series requires several yes responses before the threshold is reached, so some observers may decide that they are giving too many yes responses and prematurely respond no. So other observers may be very cautious about changing the responses and may delay too long. Indeed, the same observer at different times may commit both of these kinds of error. So the threshold is operationally defined as the mean or average of the points in each trial block at which the observer switches from yes to no or no to yes. So this operational definition is a statistical one. Okay, so a threshold defined this way, based on an observer's ability to detect a signal, is called an absolute threshold, wherein since the yes, no judgments are not based on a comparison of two stimuli but are absolute judgments about a single stimulus. The absolute threshold is a statistical concept. Much like the average taxpayer, it has other statistical properties in addition to the mean. So these are now illustrated by computing a difference threshold. So when we say a difference threshold, it is based on relative judgments in which a constant and changing comparison stimulus is judged relative to a series of changing stimuli. So the question being asked by the experimenter is this: how different must two stimuli be before they can reliably be distinguished? So in the table 6.2, as you can see, the traditional example of difference threshold requires the observer to lift pairs of weights, one weight always remaining the same. So it is also to judge if the new weight is heavier, lighter, or equal to the standard weight. So several series of ascending and descending trials are given here. So the upper threshold is the average point at which the observer changes from heavier responses to equal responses. So the lower threshold is the point at which equal responses give way to lighter responses. So next, we have the interval of uncertainty, the difference between these two values. So that's what we call the interval of uncertainty. So the difference threshold is operationally defined as have the interval of uncertainty. So as you can see in the table 6.2, this equals 10 grams. The next, we have the point of subjective. So the point of subjective, it is the mean of the upper, as you can see in the table 6.2, it is the mean of the upper and lower threshold, which is the point of subjective equality, the 300 grams in the table 6.2. So for the descending series, in this table 6.2, for descending series, the upper threshold is the mean of the stimuli leading to the last heavier response and the first equal response. So the lower threshold is the mean of the stimuli producing the last equal responses and the first lighter response. Standard stimulus is always 300 grams. So the difference threshold is one half of the interval of uncertainty, or the 10 grams in this example.
So for our next topic, we will discuss about the Weber's Law. So Weber's Law was discovered by Ernest Heinrich Weber in 1834. Weber noticed that even though you can sense a small change between two weights, when the initial weight is very small, as the initial weight is very small, as the initial weight get bigger, you can no longer detect the change. Two stimuli must differ by a constant proportion in order for their difference to be perceived. Weber's law, or the Weber's fraction as it's sometimes called, varies in size for different senses. So Weber is famous for determining a second property of the difference threshold. For a particular sensory modality, the size of the difference threshold relative to the standard stimulus is constant. So Weber's law In the Weber's law, venture called relative constancy of difference threshold Weber's law. Law is usually written as delta I divided by I equals k, where I refers to the magnitude of the standard stimulus, delta I is the difference threshold, k is the symbol of constancy. Next is the staircase method. It is a new version of the method's limit called staircase method. Concentrate responses around the threshold. So it is a newer method of limits procedure that concentrates stimulus presentation around the threshold. So next is, so this table was related to Gemini's topic about the absolute threshold a while ago. So next, let's proceed to no threshold, the theory of signal detection. No threshold, the theory of signal detection. So according to the theory of signal detection, our perception in general is controlled by evidence and decision processes. A signal or stimulus creates hypothetical evidence that depends on the intensity of the signal and the acuity of the observer, which partly determine a yes response. So, signal detection theory is a method of differentiating a person's ability to discriminate the presence and the absence of the stimulus or different stimulus intensities from the criterion the person uses to make responses to those stimuli. So, any decision you make depends on the cost and benefits associated with it. Imagine that a friend has set up a blind date for you. The cost, a wasted evening, are probably less than the possible benefits, an exciting evening now and more exciting evenings in the future. Many of us would accept a blind date, even though we knew nothing about the person we would be dating, so might be likely to respond yes. This decision would be based mostly on cost and benefits since you would lack information about the stimulus the person who is your date. Now, let us imagine a situation in which costs are high, accepting or offering a proposal of marriage. Even those of us who are eager to accept a blind date would not get married if we were offered only the information that was needed to help us decide whether to go on a blind date. The cost of an unsatisfactory marriage are much greater than those of a blind date that does not pan out. In terms of decision theory, most of us are conservative decision makers when considering marriage but liberal decisions maker when considering a blind date. This response bias does not depend on the stimulus. Indeed, the same person could be involved both instances, but only on the costs and benefits of the decision. Now, we can return to the sensory end of the signal detection. The sensory process transmit a value to the decision process. If this value is high, the decision process is more likely yield a yes response once costs and benefits have been considered. If this is low, the decision process is more likely to yield a no response, even if the cost benefits favor a yes decision. So in this figure, it shows a theoretical look at what happens in signal detection. So the sensory analysis send evidence value x to the decision module. The values of x are function of signal strength and the acuity of the observer. The payoffs, motivation, and attention process send response bias information to the decision module. Together, the sensory and the bias components determine the response of the observer. So this figure relates to my example about the costs and benefits in doing blind dates. If the value is high, the decision process is more likely to yield a yes response once costs and benefits has been considered. If the value is low, the decision process is more likely to yield a no response, even if costs and benefits favor a yes decision. Next is noise. It is a disturbance that can be confused with signals. It's always presented that when a human attempts to detect signals. This background disturbance is owing to such things as environmental changes, equipment changes, spontaneous neural activity, and direct experimental manipulation. So noise is a complex sound composed of many different frequencies. Just to make sure that the assumption that noise is present during attempts at the detection a typical signal detection experiment will present white noise, a hissing sound, such as that heard when you tune your television to an unoccupied channel along with the signal. Noise can be auditory or visual or can occur in modality we consider only the auditory system for now. So remember that signals detection theory assumes that any stimulus, even noise, produce distribution of evidence. So in the figure 6.4 shows the hypothetical distributions of the evidence resulting from noise and signal plus noise. The frequency of the impression is the y-axis and the magnitude of the evidence is the x-axis. The strength of the signal and the sensory acuity of the observer determine the amount of overlap of the two distributions. A stronger signal or a more sensitive observer would move the signal plus noise distribution to the right toward the strong end of the x-axis. So the dashed vertical lines are the mean average of each distribution. Here you can see in the figure, and the distance between the two means is called d with apostrophe or d prime. It is measure of an individual's ability to detect signals. So next is the criterion. So the position of this criterion is set by the decision process. If costs and benefits favor a liberal decision policy, the criterion will be set far to the left so that the most responses will be yes. If a conservative policy is used, the criterion moves to the right so the most responses will be no. So the criterion in signal detection, it is the level set by decision process to determine whether to say yes or no to whether a stimulus is present. So as you can see in the figure 6.5, it shows the hypothetical distributions of yes or no responses as a function of the criterion and the magnitude of the evidence. So the decision criteria determines whether a yes or no response will be made. Strong evidence to the right of criterion will lead to yes responses, and weak evidence to the left will lead to no responses. So correct detection of the signal yes responses in the horizontally striped area are called hits. So this one, the stripe area, the horizontal stripe area are called hits. So correct no responses when noise occurs. The vertically striped portion are called correct rejections. Misses occur when a no response occur to weak signals to the left of the criterion, the dotted portion of the sign plus noise distribution, and false alarms are incorrect yes responses to the noise that is to the right of the criterion. As you can see there, the black portion of the noise distribution. That's it. Next. Next is heat, as shown in figure 6.5. Correctly detecting a signal when it is presented is called a hit. So hit is the correct detection of the signal that has been presented, and false alarm is the incorrectly responding yes when only noise is presented is called false alarm. For it is the incorrect reporting of the presence of the signal on a trial in which only noise occurs. To understand more about Weber's law, please watch this video.
So this brings us to something called Weber's law. So Weber took a look at that relationship, and what it states is that two stimuli must differ by a constant proportion in order for their difference to be perceived. So in English, if we're starting with paper or if we're moving to a textbook, it kind of doesn't matter because you're going to need a certain proportion of difference for that to be detected. Okay, so that delta is difference threshold, or the JND. And it kind of depends on the medium as well. So weight versus light versus sound, you're going to have differences, but the proportion within each medium is consistent. Okay, so if you're starting with 5 pounds and I change that to 5.01 pounds, you're probably not going to notice that difference. But if I go from 5 pounds to 5.5 pounds, you might notice that. Now, if you move to, say, light, and we're looking at lumens of light, you need a certain difference there. And that proportion is going to be different than what we see for weight. And the same thing holds true for sound. So we can look at these by certain senses. And this is an average and a generalization, so it can vary as well. But in weight, you need roughly a 2% JND. In light, roughly 8% JND. And for sound, a roughly 3% change for you to detect that difference. So this is a equation that is for sure going to show up on the MCAT, so we should know this, and this is Weber's law, and we're going to walk through the 3 components. So delta I represents the difference threshold, so the JND. This means the difference from your stimulus. And the I represents the initial stimulus intensity. So what were you starting with? The delta is the difference, and you put those over one another, and you're going to get the K, which is Weber's constant. Okay? Now, let's go through an example. And this is an MCAT style question that's probably going to pop up, and we're going to present a passage or a scenario, and you're going to pull out bits of information to answer the question, and you're going to have to implement Weber's law here. So let's think of our friend little Timmy here. He's a grocery clerk, and he takes people's bags to their car and helps load them up. And our little friend Timmy, he can detect the difference between a 25-pound bag of groceries and a 30-pound bag of groceries. So if it's 25 pounds, he knows that weight. And if it jumps up to 30, he can detect that there is a difference. Okay, now, my question to you is, what's the JND? Let that marinate for a second. So the question I'm going to ask you is, if he's helping another customer, which one of these bags would he be able to differentiate by weight? We have 2 options. A 2-pound bag versus a 3-pound bag. Would he detect that difference? And the 20-pound bag versus the 22-pound bag. Okay, you with me? So let's move on, and we're going to take a look at this example, and we're going to walk through the bits and pieces that you should know. So if you were to see this, you should quit right away, and I'd ask you, what's the JND? So what's the JND? Well, did you come up with this answer? 30-pound bag minus a 20-pound bag, so there's your delta that we're trying to figure out, over the initial stimulus, which was the 25-pound bag. That gets us 5 pounds over 25 pounds. Cancel out the units, and you're left with 0.2 or a 20% difference. So what that means in English is little Timmy can detect a 20% difference in weight. And when there is that 20% difference or more, he will say, yes, these 2 bags are different. So we had 2 options, 2 and 3-pound bag. Can Timmy detect the difference between a 2 and 3-pound bag? So using the relationship that we just figured out up top, we're going to say the JND in this scenario is what? 3-pound bag minus a 2-pound bag. That's going to give us our delta over the original stimulus, which was a 2-pound bag. So 3 minus 2 is 1 pounds over the 2 pounds, which is 0.5, which is a 50% difference, which means, ding, 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 yes, little Timmy will detect that difference, okay? Now, what was our other option? 20 versus 22 pounds. Same thing. Let's walk through this. JND, 22 pounds minus 20 pounds over the original stimulus, which was 20 pounds. So that gives us 2 over 20, right? And that gives us 0.1 or a 10% difference. Will Timmy be able to tell the difference between 20 and 22? Well, the answer is no, because it's less than the JND that we said we know Timmy can detect, which was 0.2.
Receiver operating characteristics, or the ROC function. Both hits and false alarm are infrequent conservative criterion at the lower left of the curve. As the criterion becomes more liberal, both hits and false alarms become more likely, and the ROC curve moves upward to the right. The slope of the ROC function tells us the criterion. Flat slopes reveal a liberal decision. criterion generally the upper right of the curve, and the steep slopes a conservative criterion usually the lower left of the curve. The distance from the diagonal to the center of the curve is proportional to d. The diagonal represents chance performance, with the observer guessing about the presence or absence of the signal. Thus, the percentage of hits equals the percentage of false alarms along this guessing diagonal. The heavy ROC function is farther away from the diagonal than the lighter ROC function, which means that d is greater than the heavy curve than the light one. A larger d can result from a stronger signal or more acute observer. Calculating d prime. Given a set of data, we can easily calculate d prime by using tables based on the area under the normal curve. Suppose you know that the hit rate is 0.875 and the false alarm rate is 0.21. What is the d prime? First, draw the noise distribution as in figure 6.7. Since the false alarm rate represents the area under the curve from the criterion to plus infinity on the right, it equals 0.21. Since the normal curve is symmetrical, half of its area lies between 0 and plus infinity. Therefore, the area between 0 and criterion must be 0.52 minus 0.21, which equals 0.29. Now look up 0.29 in Table A of Appendix C. You will find z is equals to 0.8. This is the normalized distance of the criterion from 0. Second, repeat the process for the signal distribution shown at the bottom, the figure 6.7. Since hit rate is 0.875, this is the area under the curve from the criterion to plus infinity. Again, because of symmetry, half of the area under the curve is between d prime and plus infinity. Therefore, the area between the criterion and the d prime is 0.875 minus 0.5, which equals to 0.375. We find that an area of 0.375 corresponds to the z of about 1.15. We can now put these two z values together to find d prime in 6.8. Since the mean of the noise distribution is given the value of 0, d prime is the sum of two z values, 0.8 plus 1.15 equals to 1.95. Our calculation of d prime is now complete. Obviously, then, the larger the d prime, the greater the distance between the means of the two distributions. Therefore, a large d prime indicates either a strong signal or an acute observer. Measurement. Measurement is a systematic way of assigning numbers or names to objects and their attributes. When we assign names or numbers to objects and their attributes, we need a measurement scale which results from different measurement operations. When we measure temperature, for example, we usually use either the Fahrenheit scale or the centigrade scale. These two temperature scales are inappropriate for measuring weight, which can be measured in pounds or kilograms. So now we will discuss the properties and types of measurement scales. The properties of measurement scales. According to McCall 1990, measurement scales can have four properties, and these are difference, magnitude, equal intervals, and the true zero. Difference means that some temperatures are colder or warmer than others, and some people are male and some female, and so on. Magnitude can determine the attributes, which means that the scale can show that one attribute is greater than, less than, or equal to another instance of that attribute. Another property of attributes that some scales can determine is whether there are equal intervals between magnitudes. A 1 pound difference between two weights is same when considering both 1 versus 2 pounds and 70 versus 71 pounds. And last is the true zero. True zero meaning that zero on the scale indicates that nothing of the attribute being measured exists. You cannot have less than zero weight. It has a true 0 point of no weight, but you can have less than 0 degrees centigrade. Types of measurement scales. Psychologists use four measurement scales: nominal, ordinal, interval, and ratio. Nominal scales measure just the property of difference and nothing else. Nominal scales include zip codes, gender, the male and the female, and undergraduate measure programs. Each of these scales classifies people in some way, but they do not measure magnitude in obvious way. Thus, useful statistics such as arithmetic average cannot be used to characterize nominal measures. Even assigning arbitrary numbers to major programs would not legitimize the average major of at an institution. You could, however, determine the total number of people who major in each program. Ordinal scales measure differences and magnitude. Ordinal scales include a variety of rank measures such as how nervous people are on a 10-point scale, the placement in a beauty contest, or the finishing order in a horse race. Where you finish in beauty contest tells the magnitude of beauty, but it reveals little about intervals between the ranks. The top two finishers might be very close to each other, but the fifth and the sixth could be very far apart from each other. Averaging numbers with unequal in intervals is not legitimate. Next is the interval scales, which possess the properties of difference, magnitude, and equal intervals. And lastly, the ratio scales have all four properties of measurement scales: difference, magnitude, equal interval, and the meaningful zero. Interval and ratio scales allow you to perform most mathematical operation on them, and ordinary inferential statistics can be used on attribute measured at all levels. Most IQ measures and SAT scores are examples of interval scales because adjacent values have equal intervals across the entire scale. The 10 units of difference between IQ of 90 and an IQ of 100 is supposed to be the same as the 10 units of difference separating IQ scores of 110 and 120. Neither the IQ nor the SAT has true 0 point, so they are not ratio scales. Measures such as response speed and percentage correct are ratio measures because you can exhibit zero speed or no correct response. You should note that measurement scale derives from the measuring procedure, not necessarily from the nature of attributes being measured. Temperature measured by Kelvin scale has a true zero and it is a ratio measure. The Fahrenheit and centigrade scales, however, do not have the zero, so they are intervals. Importance of measurement scales. Behavioral data derived from different scales tells us different things, and the kinds of conclusion we can draw depend in part on the scale that we use. Because a ratio scale has four measurement properties and nominal scales only one, we have more information about something, say depression, if it is measured at a ratio level than if it is measured at the nominal level. The information provided by the scale permits certain kind of conclusions. If pain were assessed on the ordinal scale, it would be improper to say that a person with a pain score of 8 on the scale perceived twice as much pain as someone with pain score of 4. To make such statement, we would have to measure the pain on the scale that has a meaningful 0 point and equal intervals between adjacent score values, which is a ratio scales. This type of measurement scale can determine the amount of information you have about an attribute, and the type of scale determines in part the conclusion that we can draw. We now examine two approaches toward the measurement of sensation. Both approaches have the goal of devising a ratio scale of an internal psychological dimension. The first approach is Fechner's, and it's involve a reliance on the results of classical psychophysical methods to provide data of the psychophysical scale. And the second approach is more modern, one that was developed by Stanley Smith Stevens.
Fechner's law. Fechner's law relies on the research of Weber in psychophysical research. Its goal is to develop measurement scale for sensation. And according to Weber's law, the difference threshold or the differential threshold bears a constant relation to the standard stimulus. Fechner agreed to Weber's law as he assumed that Weber is correct. Also, Fechner adds two more additional assumptions and developed his own law of sensation measurement. At first, Fechner assumed that the absolute threshold indicates the point of zero sensation. By the way, absolute threshold refers to the smallest detectable level of stimulation. Moving on, Fechner assumed that the just noticeable difference or JND, which is the internal sensation evoked by two stimuli that differ by one difference threshold, is the unit defining the intervals of an internal psychological scale. As Weber's law was assumed to be accurate, Fechner then believed that all JNDs produce equals increments in sensation as shown in the picture. Each JND step on the psychological scale corresponds to the physical stimulus that is one difference threshold greater than the preceding stimulus. The first unit beyond the 0 point corresponds to the physical stimulus that is 1 JND above the absolute threshold. The next point will be 1 JND above that or 2 JNDs above the absolute threshold. To better understand the Weber-Fechner's law, let's watch this video.
The world around you provides many stimuli at a time, but you do not respond to all stimuli, particularly those which are very low in intensity. Different types of sensations need the different intensity of stimuli for activation. Gustav Theodor Fechner, the founder of psychophysics, attempted to measure the just noticeable difference, JND, with a view of achieving a higher goal, that is, formulation of a law relating stimulus intensity to sensory magnitude. He believed that the sensation cannot be compared to physical stimuli, but they can be easily compared to each other. A person can compare two of his sensations and judge whether the two are the same or different. Fechner believed that such a law could be built upon an empirical generalization first proposed by E. H. Weber, a German physiologist, in the year 1834. Weber gave an observation that the size of the difference threshold is directly proportional to the intensity of a standard stimulus. This ratio is constant. The size of the difference threshold, or the JND, is a constant ratio of the standard stimulus, which is often referred to as Weber fraction. For example, suppose that you can just tell the difference between 100 and 104 grams, then you will be able to just distinguish between 200 and 208 grams, 400 and 416 grams, and so on. Fechner labeled it as the Weber's law, which is algebraically expressed as di by I is equal to C, where di is the increment in stimulus intensity, that is the just noticeable difference, I is the stimulus intensity, the standard stimulus, and C is a constant. Many studies were conducted in the past to see whether Weber's law holds for all the sensory modalities. It was verified in most of the cases except for a few cases where the nervous system blended to notice relative differences rather than absolute ones. This law allows us to compare the sensitivities of different sensory modalities. Suppose you want to know whether the eye is more sensitive than the ear. This can be seen using Weber's law. If Weber's ratio is small, then the discriminative power of the sense modality is great and vice versa. This law helps us to understand the salient features of different sense modalities. It has been found out that using this law, the humans are keen in discriminating brightness than loudness, and Weber's fraction being 1 by 62 and 1 by 11 respectively. We have seen that Weber's law postulates that the more intense the stimulus, the more the stimulus intensity needs to be increased before the person gets a change. Fechner, with several assumptions, generalized Weber's findings which indicated a broader relationship between sensory and physical intensity. Fechner's law says that the strength of a sensation grows as the logarithm of stimulus intensity. The formula he gave is expressed as S is equal to K log I, where S is psychological magnitude, I is stimulus intensity, and K is a constant. Fechner's law makes more sense than Weber's law, as our nervous system compresses a huge range of sensation awareness into some manageable extent, and this is what a logarithmic transformation does for us. That is all for today's video. Don't forget to like, share, and subscribe to our channel Explified to get notifications about more such content.
Stevens' Power Law. S.S. Stevens is an American psychologist who attempted to develop an internal scale of sensation. Unlike Fechner, his power law is much more direct. Indirect scaling was the method Fechner used. It is a psychological scale that was built up by putting successive JNDs in a row. The observers did not judge the magnitudes of the JNDs directly, so the psychological scale values are derived from measures of discrimination. Therefore, they are indirect. While on the other hand, Stevens used direct scaling techniques in which the observer responded in psychological scale units in the first place. Magnitude estimation is the primary direct scaling procedure used by Stevens, and it requires the observer to state a number that represents his or her sensation of stimulus intensity. For example, the experimenter could present a tone of moderate intensity and tell you it has a value of 100. Then a weaker tone might be presented, so you would give it a lower number like 87. These numbers reported by the observer represent perceived psychological values directly. Next is labeled magnitude scale. To minimize idiosyncratic differences in range of numbers and used in psychophysical tasks and also prevent constriction, Bartoshuk and other sensory psychologists use a 100-point ratio scale procedure. Green, Schaffer, and Gilmore devised the labeled magnitude scale, which pairs number bounded by 0 and 100 with verbal labels. It starts at 0 value, which is labeled as nothing, and progresses through number labels of moderate, strong, very strong, and at the top of the scale is the label strongest imaginable sensation. Small and design psychophysical methods. The typical experiment in psychology measures the behavior of a large number of participants. One reason for this setup is the research participants differ substantially from one another in various complex psychological characteristics, such as personality and IQ. Furthermore, the setting in which these complex behaviors are measured may be poorly controlled. Both these problems can be handled by random assignment of large numbers of participants to the conditions. This may reduce the possibility that uncontrolled variation in people and setting will be associated with a particular treatment, which would be then allow the effects of the independent variable to be observed. An example of small n research is shown in two panels in the picture, where a single observer generated both ROC functions. Data in panel A were obtained by varying signal probability from low to high relative to the occurrence of noisy trials. The observer is conservative when signal probability is low, but as signal probability increases, the observer becomes more liberal with yes responses. This change in decision criterion sweeps out the ROC function starting from the lower left conservative, and moving along the curve to the upper right, liberal. In panel B, the experimenter kept the signal probability constant and varied the payoff when the cause of false alarm is high relative to the payoff for hits at the lower left. The observer is conservative as the relative payoff for hits increases, moving towards the upper right. The observer adopts a liberal decision criterion and becomes more willingly to say yes, there is a signal.
And for the last part of our reporting, let's summarize the topic. So, the operational definitions that specify how concepts are produced and measured are required in science, both to make experiments more public and to increase the precision of technical terms beyond their use in ordinary conversation. Next, the methods of limits, which was devised by Fechner, provides an operational definition for the concept of absolute threshold and the difference check threshold. In classical psychophysics are primarily aimed at evaluating thresholds. The more modern theory of signal detection replaces the threshold concept with two other operationally defined concepts, the D prime and beta. Sensory processes are measured by D prime, and decision processes are measured by beta. Both D prime and beta can be computed from ROC, the receiver operating characteristics, functions that plot hits against false alarm. Measurement scales result when number or names are systematically assigned to objects or their attributes. Measurement scales provide information to the extent that they measure differences, magnitudes, and equal intervals and have a true zero point. In order of increasing informativeness, the measurement scales used in psychology are nominal, ordinal, interval, and ratio. In Fencher's law probably yields an ordinal scaling of psychological judgments. Stevens' law yields a ratio scale. Next, the labeled magnitude scale is 0 to 100 scale with verbal labels for many numbers. The scale minimizes ceiling effects and minimizes idiosyncratic ranges of numbers used by different observers. Because of the tight control and relative lack of complexity of the behavior, many physiophysical experiments use small n designs that employ few subjects. Small n designs are also used because of the scarcity of special types of observers, such as radiologists. The ability to make an accurate detection decisions can be improved by using statistical prediction rules that involve predictor variables and diagnostic information. So, thank you for listening, and that's it for our report.